is the same. However, what is different and what is probably relevant for your evaluation of the device and the test is we can see the signal going into the device has no longer a crest factor of 10 dB but only 8.8 dB, because our driver amplifier in this case also operates in its nonlinear region and also compresses the signal. So the actually compression inside my device and the test itself is only a little over 1 dB. And thus also the huge difference between EVMs in single channel mode and dual channel mode. So in dual channel mode, we can clearly focus on the DOT only and exclude all the unwanted other components in my measurement setup that otherwise would have an effect on the characterization of my device and the test. So this was the live demo of the high power PA measurement where we directly compared the output signal to the input of the device and the test. And as you could see, the EVM significantly improved when we compared directly the output to the input, as well as we got a more realistic measurement of the P1 dB and also of the crest factor. Now let's go to the second demo. In this demo, we will be showing a measurement on a high gain frequency converting LNB. The block diagram looks very similar to our first example on the high power PA. So we again have some amplifying block in there. But in addition, we have here included in the device and the test, we have a frequency converting stage. Here is basically a mixer and a free running LO. The input signal again is provided by a vector signal generator and the output is fed into the FSWX signal and spectrum analyzer. Again, obviously I could do that as a one-channel measurement, simply comparing on the signal analyzer to what I am expecting the signal generator to transmit. However, the much more accurate measurement results I do get if I compare exactly the outputs of the device and the test to the input. Now, why is this example different to the high power PA example? Simply because we have a frequency converting device in there, and the two channels of the FSWX receive signals on two different frequencies. Let's go into the block diagram of the FSWX again quickly. We can again see the two signals traveling to the two signal path that is exactly identical as in the previous high power PA demo. However, what I want to highlight here is the two signal paths have two different and independent LOs. So I can tune the orange signal path to frequency number 1, which is the output frequency, for example, of my device under test. And signal path number 2 can be tuned to a different frequency, representing the input frequency of the device under test. So before we go into the measurement details, let's have a quick look at the measurement setup. Here's our high gain frequency converting LNB. It's being biased through a bias T with a DC supply voltage and receives its input signal through a coupler here on the right hand side. The coupler feeds one part of the signal into the LNB, and the coupler also feeds the rest of the signal into the RFB port of the FSWX. The output of the LNB goes through the other red cable into the RFA port of the FSWX. Now let's have a closer look at the measurements. So this is the output spectrum of the LNB at 1 GHz. We can see the modulated signal here having a bandwidth of 100 MHz. We can also see an elevated noise floor, which simply results from the high gain of the device in the test. Before we enter the device characterization, we'll have a quick look at the constellation diagram of the signal under investigation. For that, I'm using the VSA, the single carrier demodulation option, just to show you that the signal we are using here is a standard compliant DVB S2 signal with a 32 APSK modulation on it. With that, let's have a closer look at the LNB itself. So for the component characterization, we'll use the amplifier measurement personality again. In this case, we have configured it for a dual channel application only. So there is no generator connected, we don't know what the signal or the stimulus is that is going into the device under test. However, we have activated here our reference capture. So we're capturing on both channels, RFA and RFB, at the same time. In terms of measurements, I have configured a gain compression plot here on the upper left-hand side. We have a result summary plot here on the upper right-hand side. And we have a spectrum plot with the output signal in yellow and the input signal in green here. And the most exciting measurement here is on the lower right-hand side, is an absolute group delay measurement on this high gain frequency converting device with a fully modulated stimulus. So what do we see? In the gain compression plot, we can see that our device under test is slightly in compression. You can see the right-hand side of the measurement curve bends towards the lower end of the diagram. In the result summary plot, we can get an idea of the EVM, the modulation accuracy that we currently see, which is on the order of 5%. Most importantly, I want to highlight the gain, which is in numbers here 59.3 dB, so close to 60 dB. And we can also see the compression, because the output crest factor is slightly lower than the input crest factor. Most excitingly is this group delay measurement that characterizes the absolute group delay between the input and the output of this high gain frequency converting device. So what we see here is a group delay on the order of 5 nanoseconds. It's not constant over the entire channel. It varies slightly, which is expected. However, what we see is it is around 5 nanoseconds, which is roughly the average group delay of this device in the test. And again, I want to highlight that this device is a frequency converting device. So our RFB input channel is configured to a frequency of 11 gigahertz, whereas the output is configured to a frequency of 1 gigahertz. So at the same time, I can measure nonlinearities, modulation accuracy, and even absolute group delay on a fully modulated signal by using the dual channel architecture of the FSWX. So in this demo, we did measure a high gain frequency converting LNB that we drove a little bit into compression. We measured nonlinearity at the same time as we did measure modulation accuracy and also absolute group delay, all with a fully modulated real-world stimulus that the device would also see in real life. And with that, I'm going to hand over to Wolfgang.
Thank you, Florian. So, similar to these applications, you can measure phased array antennas, for example. I have shown 2 antennas here, but normally you measure directly at the beamformer IC. You can measure the magnitude and phase difference between the antenna ports. You can measure group delay as well, or any other signal. Or you can characterize a digital radio frequency memory, a DRFN. So you use a signal generator. From the signal generator, we get the reference signal, and the reference signal is measured and fed into the DRFN, and we measure the test signal coming out of the device under test. And then we can directly measure the phase magnitude change, and we can verify the FPGA programming. And scenarios like range gate pull-off, velocity gate pull-off can be verified directly in the analyzer. How to go beyond traditional borders? Wideband analyzers normally show a worse noise performance. But you have a 2-path structure, so you can make use of cross-correlation. With the cross-correlation, you can measure EVM numbers, not limited by the signal-to-noise ratio of the analyzer. You can measure spectrum, not limited by the noise flow of the spectrum analyzer. How does this work? You have a 2-path structure, so you can enable cross-correlation. So you use 1 path, but you use 2 receive paths. So you have a splitter and 2 identical receive paths. So 2 local oscillators, do ADCs, do amplifiers, whatever. The signal is the same in two paths, but the noise contribution of the local oscillators, ADCs and whatever, is not correlated. And so cross correlation helps you to get rid of the inherent noise of the instrument. And here we see the two-path structure of the analyzer. And now we go this way. We go into the analyzer and then we use the splitter and we use the two receive paths. So all the filters, the noise of the filters, amplifiers, up and down converters, local oscillators, AD converters is then cancelled. And there we introduced the RMS X-core detector or cross-correlation detector. It's a power measurement, but the averaging is done in the complex plane. And this detector can be used in the trace menu. And what is the difference? With a normal signal spectrum analyzer, when you increase the number of averages, this is the yellow trace here, the trace becomes flat, but not more sensitive. The displayed average noise level of the analyzer limits the sensitivity. Additional averaging only gives you a flat line. So the tunnel is a limit, whatever you want to measure. With cross correlation, the averaging drops down the noise level. So you get increased dynamic range, and instead of the small one here, you get a really increased dynamic range for spectral measurements or EVM measurements, whatever. And we call it RMS cross-correlation detector. It's a patented detector from Rohde and Schwarz. It works in the time domain or even in the frequency domain. And here we see a spectral measurement. The yellow trace shows the noise floor of the analyzer without cross-correlation. And applying cross-correlation, which is the blue trace, reveals a lot of spurs which are hidden by the tunnel. And a more detailed presentation or application of cross-correlation now will show Florian. So I hand over back to him.
Thank you, Wolfgang. So let's focus on the increased dynamic range that cross-correlation provides. What we're doing here is we have a device under test that we want to characterize. In this case, we do a spectrum analyzer measurement, an ACLR measurement on the output signal of the device under test. So the modulated signal goes into the device under test, gets amplified up to the nonlinear region of the device under test, and then is being fed into the FSWX, our spectrum analyzer here. So this is the DOT, and what we want to do is we want to characterize only the DOT, not the signal generator, not the analyzer, not the noise floor from any of those two, just the device under test itself. Here's again the block diagram of the FSWX. And I have again my signal that's entering the FSWX on the left-hand side, just one signal in this case. It gets fed into a splitter and then is being split up into the two RF paths. One is being highlighted here in gray, the other one in light blue. The important thing to keep in mind about cross-correlation is that any uncorrelated contribution that exists only in one path gets cancelled out if you average long enough. And the nice thing about the FSWX's block diagram here is that all the relevant components that may add noise exist in both paths. So if you have a detailed look at the block diagram, it's only a couple of switches and maybe an attenuator left to the splitter that we cannot correlate out, but all the relevant components like amplifiers, mixers, and so on, they exist in both paths after the splitter. And therefore, they can be, or their contribution can be correlated out. Let's go right into the demo. So in this demo, we're looking at the output spectrum of a high-power PA. What we can clearly see on this screen, which is configured for an ACLR measurement, 100 MHz wide signal in the center in blue, we can clearly see the adjacent channels being dominated by the nonlinearity of the device under test. So clearly shoulders in the spectrum. And I have also activated the so-called alternate channels to the very left and very right hand side on the diagram, which are pretty flat in the spectrum. The question on this ACLR measurement now is, for the alternate channels, do I measure the device and the test itself, or do I have a contribution from my measurement instrument, for example through its noise? And in order to answer that question, which is also a question of measurement uncertainty, I will now turn on the cross correlation for exactly the same measurement. Just on a side note, the current trace we're looking at in yellow is a standard RMS detector power correct measurement in ACLR mode. Now I will open the trace configuration dialog, and I will simply turn on a second trace. And for this second trace, I will activate the new RMS cross-correlation detector. As a result, on the spectrum plot, we get two traces now. Besides the standard RMS trace in yellow, we get a blue trace, which is the cross-correlation RMS detector. What we can already see is, in the alternate channels, we do see a difference between the two traces, simply because there is a contribution from the measurement instrument in these channels. On the right-hand side, the gap between the two channels is significantly, I would guess, something 3 to 4 dB. But in order to get a precise number, what I'll do in the next step is I'll change the configuration of the ACLR measurement so it makes use of the blue trace now. So instead of using the RMS detector for the ACLR measurement, I will reconfigure the ACLR measurement to make use of the cross-correlation RMS detector. All I did is change the trace to be used for the ACLR measurement, and what you can see as a result is significantly increased ACLR numbers for the alternate channel. So in this demo, we have seen an ACLR measurement, and we've also seen how we can use cross-correlation to significantly reduce measurement uncertainty, increase dynamic range of the spectrum analyzer. The ACLR measurement in the alternate channel here in this example was up to 5 dB better than with the standard RMS detector. And with that, let's go and have a demo of a second scenario. We will start with a measurement where we cannot even see a signal in the standard spectrum measurement using the RMS detector. What we'll do then is we'll activate the cross-correlation detector, and out of nowhere we'll see that there is a signal that was previously hidden in the noise floor. Let's have a look. So for this demo, I have a very simple setup. A very small in power signal is going from the vector signal generated directly into port A of the FSWX. My spectrum plot, this time I chose to use 19 GHz, and I have configured a standard RMS detector for the beginning, shows a straight line, which is basically just wideband noise. It seems there is no signal present. However, when I activate cross-correlation again on a second trace, just by selecting the cross-correlation detector on trace number 2, we can see trace number 2 in blue building up, and when it builds up, we can definitely see a modulated signal peeking out of the remaining noise floor. What I want to highlight in this example is, with cross-correlation, there is almost no limit in how much improvement in noise floor you get. The only price you pay is basically the sweep time. So I have configured 20 milliseconds as the sweep time here, and as you can see, my headline shows me 10,000 cross-correlations, which translates directly into around 20 dB of improvement. And when I reduce that, you can see the noise floor of the cross-correlation trace going up. And at the same time, the measurement speed is significantly increasing. So you can choose how much down you want to go in noise floor and in noise contribution from the instrument, at which price. Because as always in life, for each feature you get, there is a price attached, and this time for unlimited dynamic range, the price is unlimited measurement time. However, the trade-off is flexible. You can pick the sweet spot for your application. So with these cross-correlation demos, we have shown significant improvements of the dynamic range of the spectrum analyzer. You can freely choose between more correlations for higher dynamic range or less correlations for higher measurement speed. So in this demo, we have discovered a signal that was previously hidden under the noise floor of the instrument. And just to give you an example how much the noise floor can improve with cross-correlation, we have been using 10,000 cross-correlations here, and we got roughly a 20 dB improvement in noise floor. There's also a math formula behind that, which is 5 log the number of correlations. 20 dB improvement is a pretty significant improvement in noise floor. With that, I'm going to hand over back to Wolfgang.
Thank you, Florian. Cross-correlation can not only be used for spectral measurements, it can be used for EVM measurements as well to characterize the modulation quality of a device under test. For example, instead of using the noise as signal, you can use the error vector and correlate the error vector. And that helps you to get rid of the inherent noise of the instrument. In this case, we have a 100 MHz wide 5G signal, and without cross-correlation, we measure around minus 52.9 dB of EVM, and cross-correlation helps to increase the sensitivity to measure down to minus 57.5 dB of EVM, and even further. But that helps to measure really the device under test and not the instrument. Or when you want to measure phase noise. Phase noise is noise as well, and normally the signal analyzer or spectrum analyzer's performance is limited by the phase noise of the local oscillator or the wideband noise. Applying cross-correlation helps to suppress or to get rid of these noise parameters. And here you see a phase noise trace of a device under test. The gray area shows you the cross-correlation gain, and so you can even be much more sensitive for phase noise test. And this is a technique which is well known from phase noise testers. It's available now in signal and spectrum analyzers as well with a two-path structure. And here we see the instrument in detail, and during the next slides I will focus a little bit on further new methods and features we have with the FSWX. The instrument offers the unique features which we have shown already. So it's the first analyzer with multiple inputs, with phase coherent measurements on multiple channels, and it can have cross-correlation for high dynamic range for noise measurements, phase noise measurements, EVM measurements, and extended spurious free dynamic range. And you have a new software architecture. So you can easily set up a measurement with multiple channels, like we have seen. It's intuitive to activate cross-correlation, and flexible setups are quite easy. We plan to have frequencies higher than 100 GHz. Currently we start with 44 GHz and analysis bandwidth of up to 8 GHz. Another unique feature which comes with the FSWX, which is especially designed for wideband applications, is that instead of YIG preselection in the microwave range, we have filter banks for preselection for the whole frequency range. The YIG preselection normally has ripple and frequency response, and so you get rid of all these frequency response. You have a highly accurate level measurements, and you have a non-distorted IQ analysis with preselection. The YIG filter can be added for narrowband dynamic range measurements as well, but the preselection mainly is for wideband application is done with filter banks. What you see here is the level measurement of a normal signal and spectrum analyzer in the microwave range after calibration. So there's a ripple of a few tenths of dB up to 1 dB. And when you now take the same measurement for the FSWX with filter banks with preselection, you see a nearly flat line. So you get a very high level accuracy with filter banks with preselection. And you can use it for IQ demodulation. In addition, we have a fully digital sweep in the FSWX, so then really fast sweeps, much faster than standard signal spectrum analyzers. The resolution bandwidth goes up to 300 megahertz, currently limited to 50 or 80 megahertz. We have an IQ-based signal and spectrum analyzer, so similar to the traditional spectrum analyzers, you can measure ACLR, third-order intercept, whatever, but all measurements are based on IQ data. So what you can do is you can measure in the frequency domain and time domain at the same time. Or you can have scenarios with multiple signals, and you can focus on one signal and do an ACLR measurement on this signal, or an occupied bandwidth signal on a measurement on this signal. So you are quite flexible with wideband signals using the FSWX. Or you can use the two inputs. So you can measure at RFA, let's say a wireless LAN signal, and some 5G signal at input B. So you can compare mutual interference between signals. With FSWX, we start with the first instrument in the signal and spectrum analyzers, which works with the operating system Linux. So it's a quite closed system. You have less risk for attacks, or you are increased stable, but still everything is possible, remote access via VNC or device web, whatever. So all the same, but much more stable and secure. And for those who have some scripts running on Windows, we have a virtual machine, or we offer a virtual machine where Windows scripts can still be activated and be used, so that you can use your old Skippy scripts, whatever, which are in a Windows mode. The new signal and spectrum analyzer, but it's not just a new signal and spectrum analyzer, it's a different class of analyzers. So we have here our analyzers at Rohde & Schwarz, from simple analyzers up to the high-end signal and spectrum analyzers, the FSW. And the FSW is still a high-end signal and spectrum analyzer for dynamic range, for spectrum measurements, especially, where YIG filters, where high dynamic, where small narrowband filters are needed as well. But the FSWX is a new class. It's a signal and spectrum analyzer featuring multiple paths, wide bandwidth, new form of preselection, especially designed for modern applications where we have wideband signals, where we have need and sensitivity beyond what is possible with standard analyzers using cross-correlation and all these new features. So it's not just a new analyzer, it's a new class of analyzers. Hopefully, you got a good impression what new possibilities you have with the FSWX. Thanks, Florian, for showing us the live demos.
Thank you, Wolfgang, and thank you everyone for watching.
Thank you.
All right. Well, yes, thanks, Wolfgang and Florian, for that great presentation. I had an internship way back in college working in an RF test lab using what at the time were high-end signal and spectrum analyzers, and those only had a small fraction of the capabilities that are available in the analyzer you guys demonstrated today. So the advancements in the technology are really staggering and fun for me to see. So we've already got several interesting questions, but I do want to let our audience know that there's still time to submit your questions. Use that box on the right-hand side. Gentlemen, you ready to answer some questions?
For sure. Yes.
All right, well, let's get started with this first one. Are more than two input channels